Welcome, everyone. I'm excited to kick off today's presentation. Today, we're diving into the fascinating world of trigonometry. Our slide is titled Introduction to Trigonometry, and that's exactly what we'll be exploring. We'll look at the basics, key concepts, and how this branch of mathematics applies to real-world problems. So, let's get started and discover the fundamentals of trigonometry together. Let's take a quick look at the contents of today's presentation. We'll start with a quote to set the tone, then move on to understanding what trigonometry is and why it's important. We'll explore the basics of trigonometric ratios, focusing on some specific angles and their ratios, as well as complementary angles. Next, we'll work through a practical example to see how these ratios are applied. After that, we'll delve into some key trigonometric identities that help simplify complex expressions. Finally, we'll wrap up with a conclusion to summarize everything we've covered. Throughout, I'll connect each part to the overall theme of understanding the fundamentals and practical applications of trigonometry. There is perhaps nothing which so occupies the middle position of mathematics as trigonometry. This quote by J.F. Herbart really highlights how central trigonometry is within the broader field of mathematics. It's fascinating because it shows that trigonometry isn't just a niche subject. It actually forms a bridge connecting various branches of math, like geometry, algebra, and calculus. When we think about it, trigonometry helps us understand angles, distances, and relationships in space, which are fundamental in so many scientific and engineering applications. Throughout this presentation, we'll see how this middle position makes trigonometry essential, not just for pure math, but for real-world problem solving as well. So, keep in mind this quote as a reminder of the importance of understanding trigonometry deeply, as it truly sits at the heart of mathematical thinking. Let's take a closer look at the index for this presentation. First, we'll start with an introduction to set the stage for understanding trigonometry. Then, we'll explore the ratios of some specific angles, which are fundamental to many applications. Moving on, we'll discuss the general concept of trigonometric ratios, including sine, cosine, and tangent. We'll also examine how these ratios relate to complementary angles, which is a key concept in right triangle trigonometry. Finally, we'll look into various trigonometric identities that help simplify and solve problems more efficiently. This overview will guide us through the core ideas that underpin the entire topic, making it easier to grasp each concept as we progress. Let's dive into the introduction of our topic. We'll explore some important ratios related to the sides of a right triangle, specifically how they connect to its acute angles. These are what we call the trigonometric ratios of angles. It's also essential to understand how these ratios behave when the angles are at the extreme measures of 0 degrees and 90 degrees. We'll work through calculating these ratios for specific angles to see how they work in practice, and we'll uncover some useful identities involving these ratios, known as trigonometric identities, that help simplify many problems. Connecting all these points is key, because understanding these ratios and identities forms the foundation for mastering trigonometry. This will allow us to analyze and solve a wide variety of geometric and real-world problems more effectively. Let's explore what trigonometry actually is. Trigonometry is a branch of mathematics that focuses on measuring the sides and angles of a triangle. It might sound simple, but it's incredibly powerful and has many practical applications. The word itself comes from Greek origins, tri meaning three, gon meaning sides, and metri meaning measure. So essentially, trigonometry is all about measuring the properties of triangles. As we move through this presentation, you'll see how understanding these measurements helps us solve real-world problems involving angles and distances. Let's look at slide 7, where we explore trigonometrical ratios in a right triangle. Imagine a right triangle where angle A is an acute angle. The side opposite to this angle, which is BC, is called the side opposite to angle A. The hypotenuse, which is the longest side, is AC. Now, the side ob, which forms part of the angle A, is known as the side adjacent to angle A. These relationships allow us to define the main trigonometric ratios. For angle A. The sine of A is the ratio of the opposite side, BC, to the hypotenuse, AC. Tangent of A is the ratio of the opposite side, BC, to the adjacent side, OB. Cosine of A is the ratio of the adjacent side, OB, to the hypotenuse, AC. We also have secant, which is the reciprocal of cosine. So sec A equals 1 divided by cos A, or equivalently, the hypotenuse over the adjacent side, AC over OB. Similarly, cosecant is the reciprocal of sine, so cosec A equals 1 over sin A, or the hypotenuse over the opposite side, AC over BC. These ratios are commonly abbreviated as sin A, cos A, tan A, cosec A, sec A, and cot A. Notice that the ratios cosec A, sec A, and cot A are just the reciprocals of sin A, cos A, and tan A respectively. Also, an important relationship is that tan A equals sin A divided by cos A. Ultimately, these ratios help us understand how the angle relates to the lengths of the sides in a right triangle. They form the foundation for solving many trigonometric problems and connect the geometric aspects of the triangle to algebraic ratios. Let's walk through this example to understand how to find the other trigonometric ratios when given sine A. So, we're told that sine A equals 3/5, which is 3 divided by 5. This means that in our right triangle, the side opposite angle A, which we'll call BC, is 3 units, and the hypotenuse, AC, is 5 units. To make our calculations easier, we'll introduce a constant term, So, we set BC to 3 and AC to 5. This helps us keep track of the ratios clearly. Now, to find the remaining sides, we use the Pythagorean theorem, which states that the hypotenuse squared equals the sum of the squares of the other two sides. Applying that, we have 5a squared equals 3a squared plus b squared, where b is the other leg. So 25a squared equals 9a squared plus b squared. Subtracting 9a squared from both sides, we're left with b squared equals 16a squared. Taking the square root of both sides, we find that b equals 4a. Now, with all sides known, we can find the other trigonometric ratios. Cos A is adjacent over hypotenuse, so that's OB over AC, which simplifies to 4a divided by 5a, resulting in 4 over 5. Similarly, cosecant A, which is hypotenuse over opposite, is 5a divided by 3a, giving us 5 over 3. For tangent A, which is opposite over adjacent, that's BC over OB, or 3a over 4a, simplifying to 3 over 4. The cotangent A, being adjacent over opposite, is 4a over 3a, which simplifies to 4 over 3. Lastly, sec A, which is hypotenuse over adjacent, is 5 over 4a, giving us 5 over 4. So, by systematically applying the Pythagorean theorem and basic definitions of the trigonometric ratios, we've derived all the ratios from just the sine value given. This approach highlights how interconnected these ratios are and how understanding one can help find the others. All right, let's dive into slide 9, which focuses on trigonometrical ratios of some specific angles. Here, we're looking at the key angles that frequently come up in problem solving and understanding the unit circle. These are angles like 30 degrees, 45 degrees, and 60 degrees, which are fundamental because their sine, cosine, and tangent values are well known and often used as reference points. Understanding these ratios helps us build a solid foundation for more complex trigonometry problems. For example, knowing that the sine of 45 degrees is square root 2 over 2, or that the tangent of 30 degrees is 1 over square root 3, allows us to quickly evaluate and solve real-world scenarios involving angles. These specific angles are also connected to special right triangles, namely, the 30-60-90 and 40-5-40-590 triangles, which provide a geometric way to derive these ratios. Recognizing these relationships enhances our overall grasp of how angles and ratios interplay in the unit circle and beyond. By mastering these key angles and their ratios, we are setting ourselves up for success in more advanced topics and reinforcing the idea that trigonometry is a powerful tool for understanding the relationships within triangles and circular motion. Let's look at the trigonometric ratios of complementary angles in a right-angled triangle. As shown, triangle ABC is right-angled at B. We know the basic ratios. Sin A equals BC divided by AC, and cosec A equals AC divided by BC. Similarly, sec A is AC over OB, and cot A is OB over BC. Now, notice that in this triangle, angles A and C are complementary, meaning their sum is 90 degrees. So, we can write angle C as 90 minus A. Since OB is opposite to angle A and BC is adjacent to A, for angle 90 minus A, OB becomes the side opposite, and BC the side adjacent. This leads us to some interesting relationships. Sin of 90 minus A equals BC over AC. And cos equals OB over AC. Cosec of 90 minus A equals AC over BC, and sec of 90 minus A equals AC over OB. Similarly, cotangent of 90 minus A equals OB over BC. Now, when we compare these ratios, we find some key identities. For example, sin of 90 minus A equals cos A, which is a fundamental cofunction identity. And cos of 90 minus A equals sin A, showing their complementary relationship. Likewise, cosec of 90 minus A equals sec A, and sec of 90 minus A equals cosec A. Finally, let's look at tangent and cotangent. Tan A is BC over OB, and tan of 90 minus A equals BC over OB, which is also cot A. And cotangent of 90 minus A equals tan A. These relationships beautifully illustrate how the ratios of complementary angles are interconnected, emphasizing the symmetry in trigonometry. Now, let's look at slide 11, which covers trigonometric identities in a right-angled triangle. In triangle ABC, which is right-angled at B, we start with the Pythagoras theorem. AC squared equals OB squared plus BC squared. Next, if we divide each term by AC squared, we get the fundamental identity. 1 equals cosine squared A plus sine squared A. This is actually the first key trigonometric identity, showing the relationship between sine and cosine. Then, if we divide the original Pythagorean relation by OB squared, we arrive at sec squared A equals 1 plus tan squared A. This is our second important identity, connecting secant and tangent. Similarly, dividing by BC squared gives us cosec squared A equals tan squared A plus 1, which is our third identity. Using these identities, we can express various trigonometric ratios in terms of each other, which is very powerful. For example, suppose we know that tan A equals 1 over root 3. Then, applying the second identity, sec squared A equals 1 plus tan squared A. So, sec squared A becomes 1 plus 1 over 3, which simplifies to 4 over 3. Taking the square root, sec A equals 2 divided by root 3. From that, cosine A is simply root 3 over 2. To find sine A, we can use the Pythagorean identity. Sine squared A equals 1 minus cosine squared A. Substituting, we get 1 minus 3 over 4, which equals 1 over 4. Taking the square root, sine A equals 1 over 2. And finally, cosecant A, being the reciprocal of sine, is 2. So, through these identities, we see how interconnected all these ratios are and how we can derive one from the others. Thank you so much for sticking with me through this presentation. I really hope you enjoyed it and found the information helpful. Throughout this journey, we've explored the key concepts and ideas that tie everything together, emphasizing how important this topic is in our field. Remember, the main takeaway is the significance of understanding these core principles and how they can be applied in real-world situations. I appreciate your attention and engagement, and I hope you feel inspired to take these ideas forward. Thanks again for your time and interest.